And hopefully this is more of a sort of a thought exercise rather than something practical or something that you will be using like a lot, especially because arrays in JavaScript are already dynamic. So this will be just some space for us to explore what dynamic means and to hopefully also understand a little bit under the hood of how is it that arrays work in JavaScript and sort of appreciate some of that that is being done for us or without us having to think about it. So we'll start by sort of reviewing the basics of arrays. What can you tell me? What can you tell me about arrays? Anyone, just jump in, unmute yourself. What do you know about arrays?
They have an index that starts at 0.
Thank you, Maria. Yes, they are indexed and start at 0. Okay, what else? What else do we know? Anyone else?
They have methods.
Have methods. Like, what are some examples?
Like for each, filter, map.
Cool. Anything else? Anyone else? In other things, you know, we now know that they have methods.
It has a length property.
It has a length property. Length. Okay. Cool.
They have instant lookup to NDC.
Instant lookup. Lookup by index. That's right. I guess this is sort of sometimes when we talk about that, it's like the same when we talk about this index. Sometimes we might skip saying instant lookup by index and we'll just say index. But that's a good addition there. Cool.
You can loop in arrays.
You can loop through that, right? Okay. Cool. Anything else that I may be missing?
You could push. So.
Right. That's one of the methods.
And pop and shift.
That's right. Cool. What are arrays good for? Like that sounds like a trick question, but it's not a trick question. Like, what do you use arrays for? If you had to explain it to a 5-year-old, what would you say?
Like hold information.
To store data.
Okay. Yes. And tell me more about that.
I would say like it's a set of data.
Okay. You know, a set of data, and I'm gonna say, there's another word that could be a bit more accurate than a set of data.
Maybe organized.
Okay, I guess that's definitely one of the things here. This is organized in a certain order. Organized. A set of data. I wouldn't. Like this is a valid definition, as Ashia mentioned, to store a set of data. I wouldn't use set just because sets are its own thing, sort of in programming. But the things that are linked, what do we call those?
Linked list?
Linked list?
A linked list. So then this is specifically to store a list of data, right? In arrays, you store lists of things, right? Cool. Okay. Let's maybe add this one. So like here. Cool. Okay. Okay, so hopefully we're just gonna go a bit deeper on some of these things as we talked about here. So I hope to talk about the time complexity of some of the array methods, and for instance, why is it, at least for us to have a better sense as to why is this possible? How is this possible? The instant look by index. Cool. All right, so let's take a look at some of that here. So at the lowest level, an array is just a contiguous allocation of space in computer memory. This is at the lowest level. So if we could look at the memory, we could see something like this, basically. We have some random chunk of RAM that we could look at, and then there is some stuff that is being occupied by other processes here with this sort of gray or reddish. This is more like a brown color. And in some place, our algorithm might have an array. In this case, we have an array of 5 numbers. No, sorry, 6 numbers. Oh, I think I might have done some math wrong. We'll see that. 6 numbers: 90, 1, 5, 25, 70, and 10, right? And this might be, again, if we could look at the memory, this could be where our array is stored, and we have our array there. Also, the memory, the operating system on your computer is managing the memory for all the programs you are running in your computer. So, if you're playing music, this chunk of memory here might be being used by Spotify or your music application. Some other piece of memory is used by Zoom right now for holding this Zoom call, this conference room, etc. Is the job of the operating system to manage the memory, basically. And from JavaScript, or what computer languages do is like they ask the operating system, oh, I need this much memory, can you give it to me? And then the operating system will say yes or no, depending on whether there is memory available. So we can, if we had an array, when we create an array, let me open up VS Code, probably in my desktop. Oh, actually, you know what? No, I'm gonna do it in the lesson itself. So I'm gonna say, I'll share this at the end. Cool. And then here, I'm just gonna say code-s with VS Code. Put something like this. Okay. So when we study something like let array equal 9, 1, 5, 25, 70, and 10. This is going to be challenging. When I do something like this in my program, and then maybe let's console log it. And when I run this program, Node will ask the operating system, okay, give me a space for 6 elements. I need to save 6 elements, and that could look something like this if we could look at the computer memory, basically. In JavaScript, numbers occupy 64 bits in the computer memory. That's something that it's important at sort of at the beginning, but at some point we can just forget. One thing though is arrays should contain data that is of the same type. So everything should be numbers, or everything should be strings, etc. JavaScript is very flexible, and JavaScript could actually let us have the first element be a number, the second element be a string, and the third element be an object, for example. That in other programming languages we are not allowed to do. And the way, sort of briefly, the way in which that is being done in JavaScript is if instead of having the number sort of allocated there, we just have a pointer pointing to some other place in memory that contains the object, for example. But for this case, let's say an array will only have numbers, and each number takes 64 bits in memory. And we'll see why I'm making that distinction there. Any questions or thoughts up until this point? Okay. So if we know that each number, if I can go back, cool. Oh, hold on. Let me just make sure there's no way in the way. No. So with that information in mind, if we have each number occupying 64 bits in memory, then if we have 5 elements, this was the math that I did wrong. But that, here we have 60. Here we have 6 elements. I thought I had only 5. But if we have only 5 elements, we know that we'll be occupying 320 bits of memory. I guess 6 will be 384 bits of memory. And that's the space that our array is occupying in memory. Cool. So when we do something like this, cool. Okay, so you might have heard that arrays and objects, when they're passed onto functions, they get passed by reference, not by value. Where if that function modifies the array or the object, it will modify the array of the object even sort of outside of the function. That is because when we do something like this, array and then our array is really a reference to the beginning of the array. Or more explicitly, array is a pointer that is storing the memory address where the array starts. We can't see that memory address directly, but under the hood, that's what really array is. Array, is containing the memory address where the array actually starts, and from there we can get to any element. In this case, let's say our array starts at memory address 1230 or 1230. So let's say our array starts at that memory location. That I made this number up. It's not. It's a number. Just know that it's a number. If any number will do. But in this case, let's imagine that when I create an array, it gets put into this memory address, 1230. Cool. So array really contains a reference to that location in memory, and we'll see why that is sort of under the hood. So that'll be our. So that is really what will let us do something that I guess in fancy language will be pointer arithmetic. But what this really means is dealing with the indices and keying into an array. So So let's think about why is it that then we can access any element of the array in constant time. The answer is just because the computer has to do very simple math to get to any element in the array. And this is how that will happen. So, and how we're gonna learn how is it that the computer can do that and in constant time. So I think I made a few mistakes here. 9, 1, 2, 3, 4, 5, 6. Yeah, okay, no, this is good then. Okay, so let's say that our array starts at memory address 1230. Each element is 64 bits. So to calculate the position of any element, we can just use this formula, the array starting address plus the index that we want to go to, either 1, 0, or array length -1, times the element size, in our case 64, because we're dealing with just number. And with that formula, the computer then is able to calculate the address location of any of the elements given the index. So this is the example. So, we have the indices 0, 1, 2, 3, 4, 5 here, and then we have our calculations going on here. This is, again, the start address for the array. And then we want to key into index 0. So we just do index 0 times the element size. And all this math is happening under the hood. We don't, this is, again, as I said, more for a thought experiment for us to be aware of that these things are going on there, sort of for general knowledge more than anything. But then, oops, is that a question?
Yeah, so so for an array, for one array, it'll have a different address, address than array 2.
That's exactly right. Yes, whenever you create a new array, that gets a new address. Mm-hmm.
Okay.
And we don't care. We don't need to know as much exactly what that address is. But yes, it is a completely new. It's in a completely new space in memory. Yeah. Mm-hmm.
So
and we'll see an example of that. Yes.
So okay, so the formula is going to change depending on the length, right?
No.
So
this formula never changes.
Okay.
The result of the formula will change based on what index you want to visit and what is the element size. In this case, we said we're dealing just with integers, and integers in JavaScript are 64 bits.
Okay.
Cool. So here is, if we want to look at the first element, we do, that we will use just index 0, and then the computer will do this calculation. Okay, where does the array start? 0 times 64, that will be 0. And then the result address that we get for the first element of the array is the same as the starting point of the array, right? 1230. And the element that we're holding in those 64 bits is the element 90 from the array that we saw above. Right, and then the same just repeats. Index 1, we want to then sort of read the next 64 bits. And we'll do the starting address of the array plus the index that we want times the size of the element. And then that gives us the address, the memory address where the next element is, which is exactly 64 bits from the previous one. And so on. So, when you first saw arrays for the first time, you were told these are these sort of boxes that are lined up, and then with the indices you can get from one box to the other one. This is sort of like how it's being done under the hood, and then this is what lets you then do, what is the element at the last index being 5. The computer has all the information that it needs to calculate the resulting address where element at index 5 is, which in this is case 10. Because it knows where the array starts, it knows the index that it wants to go, and it knows how big each element is, in this case 64 bits. So it will just do the simple math. It returns the address where that element is, and it just reads that piece of information from there. And in that fashion, then we are able to have constant time lookup by index, because again, this is just math. Computers are really good at math, and this will take a constant time operation. Questions or thoughts on this part? So this is what that sort of looks like. You know, these are, I put the address, the addresses there, where the first one, 1230, that's where the first element is, and the, you know, from here plus 64 bits are the bits that are being occupied by the number 90. Then after those 64 bits at 1294, then we see 1 starts there, and the next 64 bits are being occupied by that one, and so on and so forth. And then the computer is just really quickly can calculate any of these addresses, and then go there, read that value from memory. Cool.
I have a
Questions, comments? Yes, Joanne.
So in this case, would you still need to find the value through the index, or do you just need to find it through the address?
So that's a good question. So us, we just need the index, right? This is just sort of showing you under the hood what actually goes on to be able to do that. The computer, you know, under the hood of JavaScript, and even under that, will go there by address. The computer will go there by address. But us, the developers, we just need to do the index, and then we automatically, you know, the computer will do the calculation for us.
Thank you.
Yeah. Other questions or thoughts?
So if you have an array that has integers and strings, for example, say like the first number is 90 and then the next index is cat, would it be, it would be the array address would start at 1230 for 64 bits for the integer, and then for the string it would be like, say, 72 bits, and then it would add from 1230 72 to get the new address for that first index?
That's a really good observation. The answer is no, because at the lowest level, we cannot have mixed arrays. Say the example you get, like let's say we have a number on the first element, and then we have a string cat on the second element. The reason why we can't have that is because then that messes up our formula here, where we use the element size. We are expecting this to be, you know, the same for all elements. And then the computer will have to keep track if it has variable like a size of elements. The way in which that's done, and the, you know, we're not going to get into it too deeply here, but the way in which that's done is that instead of the array sort of being an array of integers, and I was reading about this, and I linked it at the bottom of this lesson. What happens is actually that if you want to sort of store cat in the second element, what JavaScript will do under the hood is it will not have an array of integers. It will have an array of pointers that then will point to the other things. So something like this. If I go here, so instead of an array of integers like we have here, we'll just have an array of pointers, and then this pointer will be going to some other place in memory that holds the string cat. And all the elements here, all this, I don't remember exactly how many bits are required to store a pointer. And I guess you said like the one wouldn't be stored here. It will probably be stored in some other place that holds the value of 90. But it will not be an array of integers. It will be an array of pointers, and then maybe this other pointer is pointing to an object that says name, name Leo. So this is something that JavaScript will do under the hood if we have an array of mixed data types, which is it will turn it into an array of pointers, and it will, so that each pointer occupies the exact same amount of memory. And then those pointers will point to the actual element some other place in memory. So this string could be maybe used in some space here, and so on and so forth. Does that make a little bit of sense?
Yes.
Cool. So yeah, the elements, when I'm in a mixed array, the elements are not stored within the array, like physically in that slot of memory. They're stored pointers to other places in memory where the actual element is stored. Mm-hmm.
Question, Alejo.
Yep.
Does JavaScript do this all the time, or it's only when the data is mixed?
That's a good point. If it does it all the time, or when it's only when it's mixed. So it turns out that JavaScript, because it's an interpreted language, before JavaScript runs, there is a parsing that goes through, and then the JavaScript engines will try to figure out what you're gonna do with the array. And if they see that maybe you start an array of integers and then later on you're gonna push something that's an object, then it will start the array like this, an array of pointers. I was also reading that JavaScript might change the array on the fly. So maybe you have an array of numbers that JavaScript doesn't know you want to push an array to, and then after that you push an array or you push an object. Under the hood, that push will take a bit longer because it's going to convert the array from this to an array of pointers. Yeah, it turns out that there's a lot of nuance there and things that JavaScript is doing under the hood for us. But yeah, it will try to figure out which one will be the best way, if just an array of integers or an array that's mixed, depending on what the code is doing. And if it has to convert it at the very last minute, it will do that. Mm-hmm. Other questions? Oh, array of pointers. I forgot exactly what the space the pointer takes, but those are details that we don't have to think or worry too much about. Okay, so we have our array. We know that physically there is some. Yeah, I mean, you have all seen memory. You know, like this is the physical space. Where did it go? The physical space where your array will be, and let's see how big this is. Opening a new tab. Oh, that's big. So this is a 2 GB memory. And this is like, this is one side, and the other is the other side. But then inside of these chips, there are just electronic that's either on and off, and that's 1 bit, and then two. I should know this, but 2 GB in bits. There are. If I know how to read this number, is 1.6 with 10 zeros after the 6. Let me see. Let's try to see here. 1 GB. No, that's 2 GB. This is the number of bits that you have in that memory RAM. So that, electronics that are either on and off, and that's 1 bit. And 1 is there's current passing through it. 0, there's no current passing through it. And if you think about it, it's kind of incredible that just with that we're able to have these machines that we're all connected to and are able to code.
So that number, you can literally see like how much data is taking up your computer. Like it'll show you the physical number. Like, okay, that's cool.
Mm-hmm. Oh yeah, and now that you say that, there is the monitor, activity monitor, and the activity monitor let you look at the memory. Well, it doesn't let you see like specific addresses, but you can see here. I don't think I can zoom in here. I cannot zoom in, and this is super tiny. But it says this computer has 16 GB of memory, and right now it's using about 10.68 GB right now. So that means there's about 6 GB that are free. Yeah, and you can see here, even though this is so small, I wish it will let me zoom in, maximize zoom. Oh, that's the same thing as maximizing. Oh, sorry. Oh no, now I can't get it back. Okay, but yeah, anyway, this is all the stuff that's running right now on my computer. You can see here I'm hovering over Zoom. VS Code is somewhere there, etc., etc., etc. But yeah, okay. So the point is, these things that are inside of your computer are where that memory RAM. This is where your arrays live. This is where your objects live. All of that. And this is only, your computer wouldn't turn on if it doesn't have this memory, this RAM memory. Cool. Okay, so we see that even 2 gigs, like, I actually remember when 2 gigs was a good RAM to have, maybe like 12 years ago. 2 gigs was good. Now it's like 16, 64, etc. Okay. So that's where this number is. If we could look inside and see things, we could visualize something like this. Okay, so let's keep going here. So, okay, so let's think about like where the dynamic array comes in. Also, I should have said, like, we might not take the full 3 hours here, maybe 2.5, because this is rather a short concept. So let's think about the dynamic array. So like in JavaScript, we have the privilege of just saying array.push, and then that pushes another element onto our array, and we can just keep doing that, and internally JavaScript will take care of adding it. And that's what we're gonna learn today. How does that happen? Because it might be that you have something like this, like your array might be put somewhere where it just has exactly that space available. And the next thing that's stored after that, maybe something that Slack is using, we don't know, to store the images or to store your latest notification. then a space right next to it might be used by some other program. So here, what if we want to add a new element? Right? So you know, a dynamic array, we'll get to this again, more specific, is an array that automatically resizes. In JavaScript, arrays are by default dynamic arrays. That's why you keep pushing elements onto an array, and the array will never complain that it's full. Unless of course you just run out of memory, which in that case will be your computer crashing rather than just JavaScript complaining. So as I said earlier, like lower programming languages like C don't have dynamics arrays built in, only fixed size arrays. So basically you're asking the computer, oh, give me this many slots and I'm gonna fill them up. If we were programming in C, if we wanted an array that grows, we'll need to implement it ourselves. So this is what this lesson is about. We're gonna see what if we had to implement a dynamic array ourselves? How does it work under the hood? So here's a question. So if we have this visualization of this array, could we add one more element, say element 66 to the array that we visualize below? Yes, no, why, how? Anything? Anyone?
Can you repeat the question, please?
Yes. Imagine we have this array, and imagine we have this, it's in this place in memory, and we want to add one element. We want to add element 66 to the array. And could we do it? Yes, no, why, or how could we do that? Any position I'll take.
I think, yeah, go ahead, sorry.
Sorry. Oh, okay.
Ashia.
Originally, I had said yes, because like you can push it into the array. But then I said no, because once you push it into the array, that becomes a new array with a new element size.
Mm-hmm. Okay, yeah, so I think you're going down the right path. We're gonna have to create a new array. And so let's see, we basically have two options here. And we have this array in this way, we have two options. What we could do, and this is actually possible in C, you will think, oh, like we could just steal memory from whatever is here that's using it, and then just add an element there, basically something like this. We could just say, boom, I'm gonna steal that slot of memory, and then I'm gonna store 66 there. Well, like we can't do it from JavaScript because JavaScript is too high level and is gonna prevent us from doing that. But in C, we could do that. We could, it's kind of like the Wild West. Like you could do anything with it. And if this piece of memory that other program was using was critical, then maybe that program will crash, or maybe you will see your message disappear from Slack, or whatever was stored there gets overwritten, and then whatever was there just gets removed, and then that other process of that other program will be confused because it thought it had that space, but some other thing came and override it. So that's one thing that we might, wouldn't be completely crazy, but it will be possible. But then that will be a very mean program, and you will be a very mean developer if you're stealing from other processes. Here's another approach. I think this was what Ashia was going for. We can allocate a new array that has enough space for the elements that we have, plus the new element. So we could, if we go back here, we have like, down below here, we have enough space for that new array. So maybe we'll just copy the elements over. Let me see if I can change this color. So 90, 1, 5, 25, 70, 10, and 66. And we have our new array with the new element in there. And then maybe we just, when we had said array was pointing to this thing, what we can just do is stop pointing to that thing and now point to the new, now point to the new array. Whenever you have, whenever an array, like our old array will still be in memory, but as soon as something stops pointing to it, it gets freed, or it gets what is called as garbage collected. As soon as things will survive in memory as long as there is something in our code that's referencing it. So in that case, like that will be our array variable referencing our older array. But as soon as we update array to be the new array, then nothing else is referencing. If nothing else is referencing this older array, that older array just gets cleaned up from memory, and then we just use this new array. So that's one approach. We can definitely do that. Allocate the space for a new array and then copy all the elements over, and that's something we're actually going to do. But instead of just doing for a new element, it will be better if we allocate a new contiguous space in memory that is double the capacity of our original array, just in case we want to add more elements. And that will prevent it so that we don't have to move the array each time we append, which will be a good thing, right? Because like if we just move the array when we are appending and we're realizing that on each push, then we're going to have to copy the array to a new location and again to a new location. Better than to have some extra space there in case we need it, so that we don't have to move the array from one location to the other one very often. And that is going to trickle back into what amortized time complexity means.
I have a quick question.
Yes.
So you said that it finds more like extra space in case it grows. So if it doesn't grow, at what point does it use the space that's extra if it needs it? How does it know when it's time to use extra space?
Wait, could you repeat the question?
Okay, so there's extra space that's allocated for, like, just in case you want to add more elements to the array. So if you don't get to add elements to the array, but you need the extra space for something else, how does it know when to use the extra space or when you're going to use it?
I see. So the answer is it doesn't know. The space is sort of reserved. Okay. And nothing will use it. Nothing will use it unless it's another meme program as we talked about. But most developers and most programs are well behaved, and nothing will use that space even though it's empty. We have it allocated. We have it reserved for us. But then maybe we'll use it. Maybe we won't. Yeah, we'll see. We'll see. Hopefully that also makes sense as we move along.
Thank you.
Other questions or thoughts here?
Yeah, to kind of like, I guess, piggyback on Maria's question. So we have this new array in this new space, and we have the array pointing to that new array. Now, the old array that it was pointing to gets, I guess, deleted. So in a sense of I made the new array. I made the new array, and it's pointing to the new array. Now the old array, if I create a new array, like a second new array, could it take up that old array spot, or is that
Mhm.
illegal?
So I think if I understood, I think I saw two sort of sides or two possibilities for your question. One is, so let's say we have an array, our original array, and that's pointing to this array here, right? The one that starts at 1, 2, 3, and 0.
Mm.
This array starts at a different address. Maybe that is, no, why it's not working? Maybe this is 2374. So here we still have our array variable pointing to the old array. Once we have made the new array and copied the elements over, then we can say, okay, I want my array to now be pointing to the next array or the new array. So we'll sort of update that pointer here. So now we're pointing to this array, or I guess I should point to the number. At this point, two things could happen. This, if nothing else is pointing to our original array, then the original array gets erased, gets garbage collected. There is something in the computer that's always checking if there is something in memory that's not being used by any program and that's not being referenced by any program, that gets garbage collected, which means this space will get liberated. The space gets liberated, and then if you create a new array, then that new array could exist here. It could exist in this now blank space. Or Slack could use this space for the new workspace you add, or the new song you're playing could use that space. So that's one side. That's one thing that could happen. What you could do is, let's say you update, let's say before you update this, before you update this pointer, you say, maybe you say array 2. Array 2 will point to the original array, but in this case, I should say array 2 is just pointing to the same thing, or here, pointing to the same thing. And then after that, let's say you say, okay, now this array is now going to point to the new array. In this case, the array is now pointing to the new array, but then there is an array 2 that's still pointing to the old array, and then these two arrays are completely different. This is a copy of, array. This array is a copy of array 2, but then array 2, which is the previous array, will still survive, will still be there, and nothing can use that space. Yeah, nothing can use that space unless that space actually gets liberated, it gets freed, and the array removed from memory. Does that answer your question, Ashia?
Yeah.
Cool.
I have a question on that, Alejo. If something is pointing to only one value of the array, not like the entire array, how this will be managed? Will the whole array will be still there, or just the value?
Oh, that's a good question. So I feel like I don't really know, but I'm gonna guess that, let's say we have an element and an element variable, let's say, and we could say, well, that's pointing to this place in memory here. And if I'm understanding your question correctly, is, let's say we liberate the array and nothing is referencing the array anymore. Would 25 stop existing an element? Would it be undefined? I don't know the specific answer, but I do think that 25 will still exist. But what happens is that, primitive values are referenced by value and not by reference. What that means is that element doesn't really have a pointer to that place in memory. Element actually contains the value. So in this case, 25. And I would assume, I'm guessing here, but whenever you assign a variable, like if we do this, oops. Oh, what happened here? I hate when this happens. Let me copy it from here. So when we do say let num equal array at 0, or actually we were talking about 25, so that was 0, 1, 2, 3. So this will have 25. What I think happens is there is a new chunk of memory created somewhere else. Like let's say here, and then the element gets copied over there, and then element is actually just pointing to this thing here. Not does that make
Alejo,
yes, yeah.
is that because like an array, it's like an object, and since we have a key and value, so the only thing is gonna change is the value, is the key, and we're gonna keep the same value?
Repeat that.
I said, since they said like array, it's kind of object.
That's right.
And so it's gonna have the key and the value. We're gonna keep the values, but since like we're gonna change the array position, so it's gonna change only the key, and then.
I think it not exactly, because here, the question that Amin was asking is if 25 will survive, if something is referencing 25 and the array gets removed from memory, would 25 disappear as well? So that's slightly different from the example you're proposing, Siham, with the object. In this case, what happens is whenever so internally, and this is true for all programming languages, I think, when you create a variable like this, let num, this will allocate a space of memory for that new variable. So in here, when we do let num, what happens is that we create here, I guess the way in which we could visualize that is the way in which we could visualize that is, let's say this. When we say num, the computer will allocate some space of memory for that variable, and let's say that space is here. And then we're saying, okay, num is going to be equal to array at index 3. Array at index 3 will be 25. And the element 25 is a primitive, so it's not an object, it's not an array, it's not a set, it's a primitive, a number. And then what happens is that 25 gets copied over to that new slot in memory, and then this is really what's going on. But now you have sort of two 25s, one that lives inside of the array and another one that was copied to this variable num here. Cool. Okay, so let's keep going here. Let me see, what else do we have here? Okay, so we talked about what the options that we have. This is what we're going to do. Allocate a new space in memory that is double the capacity of our current array, so that we don't have to copy every time. So this is sort of what we were talking about. And I think here I also made a mistake where this is not really double the capacity. Wait, hold on, let me see. Okay. I should have counted more carefully, but there's an element that's missing here. Oh, but I guess I could, since I took these drawings from here where I was making them, I can just edit them here. Put this here and then put this here. So here I made a mistake where this should actually be this. Cool. So what we'll do is what we've been talking. We have our array, and when we want to push, we want to check if the array is full. If the array is full, then what we want to do is create a new array. That array could live in some other address. Again, with the specific address doesn't matter. And we allocate space double our original array, double the capacity. And then we transfer all elements from the old array to our new array. And then we add the new element here. We add it in this slot after the 10. And then what we'll say is, going back to sort of the pointer movements, is we say, okay, array, instead of pointing to this place, now just point to the new array, which is pointing to this place. And then this array gets garbage collected, gets removed. And then we have now a new array with available space to keep filling it. Does that make sense? Conceptually, what we're going to do? Give me a thumbs up if that makes sense. This conceptually. Great. Cool. All right. Let me see. What do I have here? I see. I got. Great. Cool. So let's keep going here. So then the question is, how do we do that in JavaScript? We'll write a class for that. Also, like in JavaScript, since the array won't really throw any error if the array is full. In other programming languages, when you try to add an element to the array and the array is full, you're gonna get an error saying the array is full, no more available space. In that case, we could write a function that just catches that error and then creates a new array then to then migrate. What we're gonna do here is a bit better. It's conceptually the same thing, but we're gonna have a method on a dynamic array class that will do that for us. So for this, just like we do with linked lists, or just like we do with queues and classes and stacks, we can create our own dynamic array. And again, this is more of a thought exercise than actually something you're going to be using a lot. Because again, arrays in JavaScript are already dynamic. So we'll have an array that keeps track of like our internal array. We'll keep track of the size of how many elements do we have currently in our array, and how much capacity do we have. So let's see what push could look like there. So we can have, this is the first version of push. To push a new element in the array, also I should say, for these implementations, we are not going to use any of the built-in methods like push or pop or for each, because that will be, for the thought exercise, that will be a little bit like cheating, because we know that those are already implemented. So we'll think about how to do it without those. And this is actually, again, this is the way that is in programming language like C, for example. Like in C, you literally just have the memory where the array would go, but you don't have push, you don't have pop. You have to go in and put your elements manually there. Like there is nothing, there's no helpers basically. And then, people and engineers created higher level programming languages like JavaScript, Python so that they don't have to care about all those details of C, and be able to code faster, basically. And both like JavaScript, I guess I'm not sure about Python, but you can see that if we go to, say, github.com, Node.js. Let's see, I think Node.js is, Node.js. This is actually, Node.js, you can see that Node.js is written in C++ and C. 2.6 is C, and 28.6% of the code is C++. But C++ is sort of built on top of C. And the rest is in JavaScript, which is kind of interesting. Like they're able to get, so this means that the fundamentals are handled with 50%, actually around 66% of code. And then on top of that, you can just already use JavaScript to develop the rest of something like Node. It also has some Python inside, which is interesting. But what I'm trying to appeal here is that under the hood, there's all these things going on. And you can see that Node uses C++ and C to get those things on. Okay, so we're not going to use any methods from there. So this could be like our first version. Could look like this, where we push an element, we check if the size of our array is equal the capacity. If that is true, then we can throw an error saying the array is full. We can't do that, basically. This is other programming languages that don't have dynamic arrays. This is what you will get, basically. And then we can say, okay, to add the new element, if that's not the case, we can just say this.internal array, add this.size index, which at the beginning will be 0, is equal to the element that we are inserting. And then we increase the size of our dynamic array. And here, I didn't want to use length because I didn't want us to get confused with the sort of internal array length. So I use size for conveying the length of the array. But it doesn't, it can be anything we want. So let's take a look at this here. So can we copy this? And I'm going to remove the comments. Oh, but zoom, send away. Cool. So we have an array, and then we're going to add the push method. And we just copy it from here. So we can cool. And then now from here, we already have a small array that at least we're simulating the fact that if it reaches capacity, it's going to throw an error. So let's try this out. So let's instantiate our array. Let's call it ARR equal new dynamic array. And let's say we have an array of 3, size 3. That's the size that we want to have. And then we can say array.push. Let's push 1. And let's push 2, 3. Let's try to run this, see what we get. Let me lower this a little bit. Node, and I think I call this code.js. Okay, so it didn't break. Let's console log the array size. And we see 3. We could console log the internal array if we wanted to see it, but I feel a bit bad about doing that. But let's take a look just here quickly. Cool. We have an array of with our elements there. So it works just like the real array. Now let's try to add another element. Let's try to add 4. And let's run this. Now our code is throwing an error, saying error array is full, and then it gave us where the problem comes from, basically, which is code line 10. Wait, is this true? Yeah, line 10, 13. Line 10, we have our throw error. So, any questions up until this point? Or comments or thoughts?
So we have to determine the size of the array and then push those elements into the array.
What do you mean by determine? Oh, the size, like here, yes, we will establish the size or capacity, our initial capacity here.
Okay.
Yeah, and that'll hopefully we'll see the whole picture as to like why do we want to do that. I guess we could also skip it now that you're making me think. We could also maybe start by default with an array of size 1 or an array of size 10. We could also just sort of hard code that value here and then have the array grow, because we're going to have this array grow later on. So we could also hard code like size here and then not take the size here. And then once it reaches 10, in this case so far, it will say the array is full once it reaches 10. But once we have it resizing, it will resize automatically. So I guess to answer your question, Ashia, we don't have to strictly specify the size. But that's something that I didn't think about here, and we just did it like that. Yeah, but we don't necessarily have to specify it in the constructor.
Okay.
Okay, so we have our dynamic array, and we know that it throws when there is an error. This is what version 2 is going to look like. We're just going to have it so that when we reach capacity, we call resize to create that new array, to allocate it in space. We double the capacity and move everything that we have in the previous one onto our new array. And then lastly, just add the element, basically the last index that we have so far. Okay, so let's write the resize function. So let's take a look at, so I guess like I'm gonna just write it here. So for resizing, we need to calculate double the capacity. So I'm gonna say let maybe new capacity is equal to that capacity, the all capacity times 2. And then I need to allocate a new array with this capacity. How can I do that? There's a few ways of doing it. I mean,
you declare a variable and you do equals array, a new array, and you give the new capacity as an argument for it.
So I just can literally create a new array with the new capacity here. And this will be, under the hood, this is performing the action that we were talking before about going searching for a new space in memory that will have this capacity. And once the operating system finds that place, it returns it to a program. Our program can start using it. So we have our new array with double the capacity. Now we have to copy all elements from our previous array to our new array. How do we do that? Somebody else? I want to hear maybe from Ohidor. How can we copy the elements from one array onto the other one? Ohidor, are you with us? Maybe he stepped out.
He typed in something in the chat.
Oh, okay. Thank you. I can't see the chat. Where? Okay. Does anybody else want to go? Wants to go take a stab at copying the elements from one array, the previous array, to the new array? Join.
Let's say you could have like a variable and then use a spread operator.
Yes, we could use a spread operator, but let's say we can't use a spread operator. Or we cannot use any of the built-in methods or fancy stuff like the spread operator. How could we do that?
In a regular loop.
Yeah, the for
Okay.
loop.
Okay. Siham, do you want to guide me?
Yeah. So what we can do, we can do the for let I equal to 0, and then I is less than. Usually we do length, but since we have size, you're gonna do this size, and then I plus plus. And then we're gonna say new arrays. Since we have a new array, so we're gonna do the new array at I is gonna be the array. So this and this internal array at I, maybe.
That's correct. Okay.
And then we should, after the line 23, we have to this internal array, it should equal to the new array. Yeah.
And I guess we should also update. We should also update the capacity of our array because now we have a new capacity.
Okay.
So let's do that with just updating this capacity equal new capacity. Cool. And then this then will copy the elements over to our new array. And here is this line is what is doing that conceptually where I was drawing with array no longer pointing to the old array, now array pointing to the new array. This is like literally this line conceptually executes that step of sort of unlinking or stop referencing the previous array and now pointing to the new array, which causes the previous array to get garbage collected. And then we just update the capacity. Cool. Any questions or thoughts about this? Does this make sense to everyone? Thank you, Siham. Okay, cool. Great. So we have a function to resize. Let's verify it against this one. Yep, great. Exactly the same. So we have a resize. So now let's update our function here, push, to instead of this dot size triple equal this capacity throwing an error, we can just do this dot resize our array. And then anytime our array reaches capacity, we'll resize with double the capacity. And then you will add the element at the end and increase the size after that. So now we have a dynamic array. If we have, let's push 5, 7, 6, 7. So here's a question. What will be the array size, and what will be the array capacity for these once they console log?
I think the size will be 7. And the capacity will be 8.
Okay. How do you arrive to that 8?
To 3. So
okay, so we know that here, like this will cause a resize, right?
right.
And our new capacity will be how much?
8.
At this step, it will be 6, and at the end, it will be 12.
So at this point, we double the capacity. Our previous capacity here was 3.
Okay.
Then we double the capacity.
So it's 6.
That's 6, and then we add these other elements. This one is still good. We have capacity for a 5th element. We add capacity. We have capacity for a 6th element. This is our new capacity. And then here we push 7. At that point, we no longer have capacity for 7, but resize happens again. And then now what is the size, Ashia?
12.
Mm-hmm.
Oh, you got me. Okay.
Oh.
I thought we doubled from after, like, okay, so I thought we doubled once we pushed the new element in. Like, so we started at 3 and then we pushed in 4 and then we doubled that 4 to get to the new capacity. But I read it, I was doing it wrong. We double the previous capacity, the original capacity, then we push in the element, then we continue to push in elements until it gets full, and then we have to resize again and then double the second capacity that we had.
That's exactly right. Yep. Other questions or thoughts, anyone? So to the question that Ashia made earlier, like we could skip this, we could skip the capacity here, or the initial sort of size, as long as then maybe we do this. New array, we don't do that, or maybe we start with a 1, and then capacity is 1, and our array should still work. Let's try it out. We have capacity 8. We have size 7. There was another resize here, right? In this case, because we started with 1. Wait, sorry, not here. No, yes, here. Resize, and then the new capacity here. Oh, I guess where the resizing happens changes in this case, because we have new capacity being 2. Well, let's think about this. And then after that, we do 3. So this will cause another capacity here. Oh, what was that? That's some code. Here we have another resize where the new capacity will be 4. Then this one doesn't happen there anymore. That one will happen here, and the new capacity here will be 8. And this one won't happen there anymore. We see that the last capacity will be 8, and we have 7 elements. Does this make sense?
No, I didn't understand this.
Okay. So like the only change that I did was stop passing a size in the constructor. So that maybe we have like, we don't want to specify, or we don't need to specify the initial size that we want to do, or the initial capacity that we want our array to have. So in that case, we could just initialize our array with an array with only one element, or with only one slot. And then our capacity is just one. But because we have a dynamically resizing array that will check as soon as its capacity is reached, it will resize. Then we see that the resizing is still working, because when we push one and then we have capacity for that, our capacity is one. We hard-coded our capacity to one to start off as, which is fine. And then we push two, but for that one we no longer have capacity. So then a resize happens there, where the new capacity will be 2. And now our array is able to hold 2 elements. It was increased, it was double the capacity. And then after that, we push 3, but we don't have capacity for 3 because our current capacity is 2. So our capacity gets double by the resize, and now our new capacity is 4. Then we push 4. We have capacity for a 4th element. Then we push 5. For 5, we no longer have capacity because the previous capacity was 4. 5 will then, when we push 5, we call a resize, which will then double our capacity from our previous capacity. Our previous capacity was 4. Now, when we push 5, the capacity gets double, and now our new capacity is 8. And we push 6 and we push 7, and there is room for those. There is capacity for those elements there. So our final capacity in this case, when we push 7 element, is still 8. We have space for one more element, and we currently have 7 elements in the array. Siham, did that work?
Yes, thank you.
Cool. Other questions or thoughts? So I think with this, we might start noticing a pattern where if we do 8 and we do 9, let's say, so this will cause another resize. What's going to be the new size? Sorry, the new capacity at this point. Let's see. I'm going to ask from one of you. Brutus, what will be the new capacity here? Bruce, are you with us? Oh, I see Kong responded.
Yeah, it would
16,
double.
that's right. It doubles. It doubles. So this will keep doubling like that. And the resizes will happen less and less often. Right? Do we see here how like here the resizes happen almost immediately, one after the other one. Then here now we have a space. And then the resize between 8 and 16, we have some extra space. And then for the next resize, which will be 32, we're gonna have a wider gap when the resize happens. So that is important for the amortized time, because let's just jump there. So, okay, I guess like let's think about the time complexity of this. And this is the time complexity of the push method on your arrays. When we push 1, what's the time complexity of that?
Oh, 1? Oh, yeah.
Of 1, that's right, constant time.
Constant time.
Of 1 or constant time, those are 2 good answers. When we push 2, what's the time complexity of that?
Same is constant time.
This one is actually not constant time.
Because we're resizing.
And we'll see what, because we're resizing, right? So we have to copy all the elements from the previous array onto a new array. So that makes it what? Time complexity.
Or the n.
Of n, that's right. And this one has to loop to create the new array gets allocated, and it has to loop to copy the elements to the new location. This one also has to copy the elements onto the new location. This one, what's the time complexity of pushing 4?
Constant, because we're not doing anything.
That goes back to constant because we're not resizing. We're just, if we look at here, when we don't have to resize, which is when we still have room, we still have capacity, we just use size as an index so that we go on and that index and insert the element there, and then we increase the size. That's right. So this one is constant time. This push is constant or linear?
It's going to be linear because we're resizing.
Okay.
So we have to look.
We have to look, a new array is created, and so on. These 3 are constant time because we're just going directly to those indices and adding the element there. This one will be linear because we're resizing. So when we're resizing, we create a new array, we copy the elements from the previous array onto this new array. But what amortized time complexity means so push, we say, if we want to be extra accurate, we will say the time complexity of push is amortized constant time. The amortized means that this linear time will not happen very often. As the array keeps growing, we're going to see less and less resizings. And the great majority will be constant time insertions. So then that's why we say amortized constant time. Like you can think of the time cost of each special doubling a pen, which is when we're resizing, is O of n. But at the same time, the number of constant operations you get until the next doubling also doubles. I guess like this is, this is can't see it very clearly here. Let's see. Oh, actually, instead of this. So the next one will be, let's say 10. Oh, yeah. Like I'm gonna have up to 32 until it has to resize the array, right? And actually, yeah, I'm not gonna do. Oh wait, hold on. 16. Here we
have to resize in there.
Actually, we don't have to resize here. We resize on
17. 17, no?
Mm-hmm.
Hello， 你到了？15 OK， 我知。我就睡着嘅。
Is that who's that?
Oh, sorry, it was me. There's a phone call coming.
Oh, got it. No problem. So 32, and now we're doubling our capacity on each time. So which what in plain language what that means is whenever you're adding an element to an array, most likely you're gonna be on the constant times. From time to time, you're gonna have a resize, which is gonna take of n or linear time. But as the array size grows, you're gonna be less and less likely to reach to have an insertion that's O of n. So then that's why we say inserting into an array or pushing into an array is amortized constant time. we could think of it as sort of it cancels out. The average, we can say that a pen has an average cost of, or amortized cost of constant time. And given this, in our industry, we usually just wave our hands and say dynamic arrays have time cost of 1 for a pence. Though strictly speaking, that's only true for the average case or the amortized cost. Because again, most likely when we put something into an array, we're more likely to fall in here than on the resizing ones. But from time to time, we're gonna get to a resizing one. Does that make sense? Thoughts, questions, comments?
Question, do you do the opposite operation when you pop? Like, do you shrink the array as well?
That's a really good question. I don't know. I would think so. It feels, I didn't think about that for this exercise. But I think let's do a Google search really quickly. Actually, also dynamic array. This is sort of the same concept here. Let's try to search for reduce. We have, I think that's a really good question. I don't have the answer for it right now. Let's do reducing size dynamic array. Let's see what we got. Oh yeah, I mean, this doesn't say anything about that, but this does say these are functions that if you're coding in C, you have to call, these are the functions that you call to actually allocate the memory. And you pass how much memory do you want. So I think I don't have a good answer for that question. I mean, I'll say it will depend on all of this is dependent on the use case, or what are you going to use this array for. If you have an array that is going to change the length a lot, and on top of that you are constrained on space, then you want it that when you remove element, don't waste that capacity there, and you resize it back down. Just like in the same way that this is a solution to the problem of what if we want the array to resize itself, because that's a nice feature to have to keep growing. Oh, you know what? Also, let's do, so this type of array in Java has a name called array list. I was looking at the documentation. Let's see. Resizable implementation of the list interface implements all optional operation permit all elements. Reduce. Reducer. Now, I'm not sure how. Like, we'll need to look through all of this to see if these guys also decrease the size. I will kind of think so, because like the resizable array, like I will assume that that's like both ways, but I'm not 100% sure. Other questions or thoughts? Okay, no questions. That's fine. So let's take a look at some of the other operations. So for instance, we want to get by index. we could do something like this. We could implement a get method that looks like this. Get, we pass in an index, and we say if the index is greater than the size, we can throw an error that says index out of bounds. Otherwise, we go into our internal array and return that element at that index. And let's try to see, let's try to use this one here, console log. Array.get. Let's get the 10th element, or the, actually not the 10th element, this the element at index 10, which is the 11th element. Let's run this. Capacity. Oh wait, hold on. Is this correct? 12.
Yeah, it's fine because you don't have 10.
Oh, I skipped 10. That's very smart on my part. Oh wait, so then that means let's fix that, because then that means my allocation is 11, 12, 13, 14, 15, 16, 17. Cool. Now we get 11. That's the element at that index. Oh, let's think about this part, like removing. And this is where we talk a little bit about the time complexities of removing, for example. So if we want to implement a function to remove the element, and let's say we're going to do an index. What we need to do conceptually, what we'll need to do, let me draw it here. Let's say, I guess let's do it here. So here, if we want to remove 26, then I hope you already know this. Let's say we already copied the element. So that's there, like this one doesn't even exist anymore. This is complete on. All right, it's just this. So if we want to remove 25, what will we need to do conceptually? Who can tell me? In here, with this drawing.
Probably copy 70 to 25, then 10 to 70, then 66 to 10, and then
That's
nothing
exactly
to
right.
66.
Thank you, Amin. That's exactly right. So we're going to move 70 to 25, 10 here, and here, and then we're going to erase this spot, or clear that spot, so that then we override 25, we put 70 there, 70 we override with 10, 66 we override 10 with 66, and then that space is empty. So the way in which you can do that is what we have here, basically. Let's take a look at this. Oh, I guess you don't need that. Cool. So that basically that's what this code is doing. We go to the index, and we go to the index that we want. We start I there, then we check for as long as I is less than the size. As long as the I is less than the size, we increase I, and we're just checking as long as the current element or the next element is not equal to undefined. That is, that's when we are here. We have all this space that's available. As long as I plus 1 is not undefined, what we'll do is we're going to make internal array at I equal to internal array at I plus 1 to effectively do what we were doing there. Oh, I guess one thing that I realized with this is 66.
I believe
Oh,
if you Yeah, if you skip maybe the condition on 38, it will be fine.
You'll be fine. Let's take a look. Let's take a look here. Remove. I'm gonna comment out these lines, and here I'm gonna say array.remove. Oh, and also I should have returned the element. Return the element we're removing generally. Let's come back to that. Let's remove 3, which is at index 2. Console log. And I know that it's not returning anything yet. And let's console log. We're console logging the size and the capacity at the bottom. Let's try this out. Oops. Index out of bounds. We're getting index out of bounds. There's an error in my implementation here. Wait, let me see what it's throwing at. Index out of bounds, line 31. Oh, that's this guy here. Cool. So we remove undefined. We see capacities 4, sizes 4, and the capacities 4. That's right, because we push 4, and then after that, our capacity is full here, and then we remove 3, which is at index 2. And then after that, I push 5. The question that we wanted to look at is what happens with the array? 60 is 4 still there. We have the duplicate 4. Let's see. Array, that internal array, so that we can see it inside. Yep. So we have that extra 4 there. But this is actually not a problem because we did decrease the size. So whenever we push again, this one gets overwritten. When we push 5, now 5 takes that place because we're using size as to like where do we keep track of the sort of the end of our array. Yeah, we could still like if we wanted, we could make it a bit more explicit and set it to null or something. Oh, but also we forgot to return. It should return the element that we are removing. So maybe before we override it, we need to say let element equal this that internal array at that index. Another issue that I'm noticing with this implementation is that we should also check here for the bounds of the array, for instance. So let's say if index is greater than this dot size, throw an error. Index bounds.
Isn't it greater or equal?
Let's think about that. Greater or equal?
Yeah, because this dot size is pointing kind of to the next one, the next available one, right?
Yeah, but let's see. When we have no, it has to be less. It has to be like this because when we have 3, or maybe I'm wrong. Let me double check. We have 3. The size is 3, but the indices we have available is 0, 1, 2. So at this point the size is 3, right?
Yeah.
Right. At this point the size is 3. At this point the size is 4. And if it's greater than, if it's greater, yeah, so if we try to remove the element at index 4 here, we don't have that element. That will be an index out of bounds. Does that make sense? I mean, cool. So then the element I can use return element here. You know, I guess if let's do it like this, so it's a bit more separated. Let's try again. You know, we remove 3, and then this was before we push 5. The 4 was still there, and then we push 5, but you know our size is keeping us sort of here, and then when we push 5, 5 overrides that 4. So I feel like that's fine. If we wanted, we could also just override this part here, saying something like this dot internal array at this dot size equal null, and then we decrease the size. See this? Oh wait, actually, I should do this after. Oh, but I'm not thinking the larger picture. This will give me some more issues. Yeah, we could just set that last one to null. We update the size, we reduce the size, and then we say the previous element there, we just set it to null, so that to signify that's empty. Cool. Any questions or thoughts?
So if
Yep.
the size is 3, the index will never be 3. Because
That's right.
So why wouldn't it be if index greater than or equal to this dot size?
Hold on, I feel like I am the one that's confused. Let's try this. I guess let's console log all here so that we know what's going on. So let's try to remove 4 here. But again, we're removing the element at index 4, but there's no element at index 4. So this should throw an error saying index out of bounds. Oh, okay, but it doesn't return the error. It returns undefined. So yeah, okay. Now I see what Amin was pointing at. Then this does have to be greater than or equal to the size. Yep. Cool. Thank you. Yeah, I feel like I was not thinking straight here.
Yeah, it's a bit confusing, like those things.
I still have to think about those details. Cool. Thank you, Ashia, also for bringing it back. Cool. Other questions or thoughts? So this is pretty much it. This was what I wanted to show you today. And to know that array that you do on JavaScript, somebody had to create something like this under the hood, and it's definitely better than what we're doing here. But somebody had to think about that because they came to that problem where what if we want arrays to resize themselves? How do we do that? And then this is how we could do it if we didn't have dynamic arrays in JavaScript. As a thought exercise, I would recommend. I'm gonna share this code. I'm going to share this code into the, I'm going to share this code in the code share channel. Oh, also, let me show you here how you can share code, because Slack has changed from the time I used it. And before it was a bit easier, but now if to share code here, you have two ways. One is you could do triple backticks, and then that lets you do console log. That lets you do this code here, but it doesn't provide any syntax highlighting. If you want to write syntax highlight, you can go. No, it's not a touch file. You see that it changed. Now is this shortcut thing here, and then create a code or text snippet. And then these things open up, and then you can paste your code here. And then I'm going to say dynamic array.js. And then here I can select, supposed to add a tag, but that doesn't seem to be working. Put JavaScript, and that enables the syntax highlighted code from lesson. Just as a message, create a snippet. Once you do that, then it's shared, and then it's a bit nicer format with lines, line numbers, etc. So I just shared that code as a thought exercise. It will be helpful for you if you try to implement these methods, given the restrictions of the dynamic array. Again, without using like the actual pop, or without using the actual slice, without using for each, without using the actual map. Like how would, this will force you to think about how are those implemented under the hood. Yeah, I guess also we did talk about remove, but the time complexity of remove. Who wants to say what the time complexity, or attempt what the time complexity of remove is? Let's see, Maria, what do you think?
I'm thinking it's O of n, linear.
That's correct, linear time. What would be the worst case scenario where this loop is the longest, or has to loop the most when you're removing one element? If we're thinking back here where this moving has to happen, how many, in this case, okay. In this case, when we have,
sorry, I was about to say the first one, because you have to do like the loop all over, like from the beginning. And the best case is the last one.
The best case is the last one. The worst case is the first one. Because here, when we're doing 25, how many shifts do we have to do? We have to do 3 shifts from here to the end. But if we do, if we want to remove 90, then we have to do more shifts, because we have to move this one here, then this one here, and the rest, and this one here. So then now it's 6 shifts, right? So removing an element from an array with, for instance, with slice, with splice will be a linear time operation. And remember that time complexity, we're generally talking about the worst case. Yeah. Other questions or thoughts? All right, cool. We can leave it here for the night. Again, I think it will be helpful if you try to implement this, add them to this list, or even more. I feel like, for instance, I didn't include slice, concat. Those will be cool to implement here in this custom data structure we started here, being the dynamic array. I linked to a few resources here. This one was cool, was very concise about everything we talked about. This one goes a little bit more into detail about like how JavaScript implements arrays. And that was also kind of cool exploratory resource. But if there's no any additional questions, we'll leave here for tonight.
Thank you, Alejo.
Thanks, Alejo.
Thank you. This was great. Thank you.
All right, you're all very welcome. If you have any questions, I'm sticking around for the rest for an hour. So feel free to drop me a line on Slack if you need help with anything. If not, I'll see you. Oh, I should also say I'm gonna be off next week, but I'll be back after that. So we won't have any programming for like the next week. And so our one-on-ones, I'll make sure to cancel those, but I'm coming back after that week. So I wanted to give you guys a heads up there. Cool.